Have you ever tried to read a blueprint that just vanishes the moment you shine a light on it? Well, that's the kind of puzzle at the heart of quantum computing. Every single time we try to look at quantum information, we risk changing it completely. So, how in the world do we map out this invisible world? Today, we're going to pull back the curtain on the amazing blueprint scientists use to do exactly that. To really appreciate the genius solutions we're about to see, we've got to understand the problem itself. In the quantum world, you're faced with two core mysteries that seem almost impossible to solve. So here it is, the central dilemma. Someone hands you a single qubit. What state is it in? See, it's not as simple as 0 or 1. A qubit exists in this delicate dance of possibilities called a superposition. The very instant you measure it to get an answer, you risk collapsing that whole dance, destroying the very thing that you were trying to see. It's a fundamental roadblock. Now, this big question really splits into two different kinds of missions for our quantum detective. On one hand, you've got quantum state discrimination. Think of it like a multiple choice test. The state has to be either A, B, or C, and your job is to figure out the perfect measurement to just pick the right answer. But then you have quantum state tomography, which is way more like quantum forensics. Here you've got thousands of identical copies of a total mystery state. By measuring each one in slightly different ways, you start to piece together clues, build a complex profile, what we call a density matrix, to get a full picture of the original. Okay, so with those huge problems on the table, where do we even start? Well, to start understanding how quantum states are supposed to change in a perfect, clean textbook world, the rules are actually surprisingly simple. In an ideal world, every single thing you do in a quantum computer is this perfect reversible transformation. We describe this with a mathematical tool called the unitary matrix. The best way to think about it is like a precise, totally predictable rotation of a quantum state. No information gets lost, and you can always run the rotation backwards to get right back to where you started. It's a clean, perfect model. But here's the catch. Real quantum computers are not perfect. They are noisy, stray magnetic fields, tiny changes in temperature, even just slightly imperfect hardware. All of this stuff can mess with our delicate quantum states. These messy real world processes aren't just described by those simple clean unitary matrices. So what do we do? To deal with this messy reality, we need bigger, better, and more powerful tools. And that tool is called the quantum channel. You can think of it as a universal language for all quantum processes. It's a mathematical framework that can describe anything that can happen in a quantum state, a perfect operation, a random error, even the act of measurement itself. It can handle the whole shebang. Now, to really get a handle on these quantum channels, scientists have come up with three different but equally powerful mathematical ways of looking at them. It's kind of like having three different blueprints for the exact same machine, where each one reveals a totally different but crucial aspect of how it all works. And here they are, the three main characters of our story. These representations are named after the absolute geniuses who developed them: William Stinespring, Karl Kraus, and Manduin Choi. Each one gives us a unique and incredibly powerful way to look at the very same underlying quantum process. Let's start with Stinespring. I love this one. I like to call it the physical recipe because it gives us the most intuitive physical picture of how quantum channel actually works. It basically tells us how we could, in theory, build any channel from scratch in a lab. This recipe reveals that something absolutely incredible, that any noisy, messy, imperfect process can be thought of as just one part of a much bigger, perfect operation that we're only seeing a piece of. The steps are pretty straightforward. You take your system, you add a fresh workspace system to it, then you do a perfect reversible operation on the whole thing. And then you just ignore the workspace. The noise, all the messiness we see, is simply the information that gets lost when we discard the extra piece. And that right there just brilliantly shows the power of Steinspring's insight. It gives us a universal recipe. No matter how weird or complicated a quantum process might seem, we know for a fact there's a standard physical way to build it. That is truly a profound idea for understanding where quantum noise even comes from. So, a physical recipe is fantastic for building your intuition, but if you're a quantum engineer trying to simulate a process on a computer, you need a formula you can actually plug numbers into. And that's where the cross representation comes in. It's the whole operational workhorse. The cross representation gives us the direct formula. What it says is that the final state is just the sum of all things possible that could have happened. You can see it in the equation there. For each possible outcome k, you take your starting state, which is rho. Then you sandwich it between a special matrix called a cross operator, a sub k, and its partner. You do this for every possible path. The noise could send your state down, and then you just add up all the results. This is a practical computational recipe. So we have our physical recipe and our operational formula, but there's a problem. A big one, actually. It turns out many different Stinespring recipes or many different sets of cross operators can all describe the exact same channel. So, how can we be sure if two different looking descriptors are actually identical? We need some kind of unique identifier, and the Choi representation solves this problem perfectly by creating a unique, unforgeable fingerprint for every single quantum channel. It's a single definite matrix. If two channels have the same Choi matrix, they are the same channel. End of story. This gives us an incredibly powerful way to classify and compare any two quantum processes with absolute certainty. And get this, the way you actually create this fingerprint is just beautiful. You start with two particles that are perfectly linked together in what's called a maximally entangled pair. Then you feed just one of those particles to their channel. The final combined state of both particles that becomes the fingerprint. It's amazing and it reveals this incredibly deep connection between quantum processes, noise, and the very fabric of entanglement itself. So we've got the physical recipe, the operational formula, and the unique fingerprint. How do these three amazing blueprints come together to form the ultimate toolkit for a quantum engineer? And finally, to crack the case for a quantum detective, this table just lays it all out. These three representations aren't competing with each other. They're totally complementary tools. You use Stinespring to build your physical intuition. You use Cross to run the calculations and simulations, and you use Choi to verify and classify everything. Together, they give you this complete 360 view of any quantum process you can imagine. And this brings us right back to where we started. By having these perfect blueprints for any process, including all the noisy, messy ones, we can understand exactly how quantum information is getting transformed. And once we understand that, we can mathematically design the perfect optimal measurement to pull out the information we need. And just like that, we solve both the state discrimination and the tomography problems. Case closed. Ultimately, these tools aren't just about understanding noise, they're about mastering it. They're not for controlling it, they're correcting it, and maybe even using it to our advantage. They are the absolute foundation for things like quantum error correction, for brand new algorithms, and for the whole future of quantum technology. So, the real question these blueprints leave us with is now that we can finally draw the map of the quantum world, what are we going to build with it? Thank you for tuning in to another episode of Quantlock.